We've probably all had to take medicine at some point in our lives, whether for a headache, allergies, an infection, or potentially something more serious. Have you ever thought about what happens when you swallow a pill? A tablet might seem like something that's pretty small. You can hold it between your fingers, and it sure doesn't weigh very much. Even though it seems small, each one of those tablets can be up to 10 million times larger than one of the individual drug molecules that it has to deliver in order to help you with whatever issue you're trying to fix in the first place. That's a huge size difference between the drug molecule and the tablet that it makes up a tiny part of. How big a difference is it? Imagine that you're the size of a molecule standing next to a proportionally scaled statue of a tablet. The tablet statue would be 4,735 miles wide and over 1,800 miles high, and could cover the entire continent of North America. That's a big tablet. In order for a drug to work in your body, though, the tablet given to you by your doctor has to get broken down to that scale before the individual drug molecules can go to work. So why does the medicine that we take need to get broken down into individual molecules? Well, that all has to do with how a drug molecule gets into your body in the first place. Did you know that when you swallow a tablet, the drug isn't inside your body yet? It sure seems like it is. I mean, you can't see it after you swallow it, and just like food, the tablet ends up in your stomach, which is inside your body. When we swallow something, it begins a journey through your body's internal plumbing system, which is essentially a hollow tube running through your body called the gastrointestinal tract. The tablet is carried along in an acidic fluid which contains things that the body uses to help us digest food and other things that we swallow. As this fluid moves from the stomach into the small intestines, muscular contractions help mix up all the contents, breaking things down into smaller and smaller sizes. Your small intestines are the first stop along the way after things make it through the stomach. This cylindrical tube is approximately the same width as a quarter, and it twists and turns, filling much of the space inside your abdomen. Did you know that your small intestine is so long that if it was unraveled, it would stretch approximately 20 feet in length? What's most important about your small intestines is that the inside is lined with tiny little finger-shaped folds, which themselves are lined with even smaller tiny finger-shaped folds that stick out into the fluid as it washes by with its contents. These are called villi and microvilli, which because of their size provide an enormous amount of contact area with whatever is in your intestine. Even though you can't see or feel these villi and microvilli, they're there, and they're important. Did you know that the extra area that they provide for contact with the intestinal fluids is roughly equivalent to a tennis court? Think about that the next time you play tennis at the park, and it's all inside you. Running inside each of these tiny little cells are branches of your circulatory system or your bloodstream, and that's where we need to get the drug molecules to. You see, the blood is how the body gets the drug from one part to another. Let's say you took some medicine to help with a headache. That drug has to make it from your stomach and intestines all the way up to your head, and your blood is how it gets there. In fact, your blood is how the drug gets everywhere in your body. This is what makes the size of the drug molecules so important. Tablets are just too big to get across the barrier. For that matter, so are particles. It would be like trying to squeeze a basketball into a drinking straw, only harder. Only individual drug molecules with their tiny size can pass through these cells in the small intestines and be carried by the bloodstream. So somehow, those tablets that you swallow need to be designed to allow this to happen. How this is done comes from how a tablet is designed. Tablets are made by taking dry powders, mixing them together, and then compressing them under tons of pressure to make those powder particles stick together. In any given tablet, only some of these particles will contain drug molecules. Other ingredients, called excipients, are included so that the final tablet behaves the way that it's supposed to. Some of those components are there to help hold the tablet together when it's made. Others are there to help the tablet begin to break down after you swallow it. Although these excipients don't play the same role that the drug does in helping your body medically, they play an essential role in making sure that the drug molecules can. Picture a tablet like a stained glass window, where the green sections represent particles containing the drug, while all the other colored particles all have some other purpose for being there. Like we said, making a tablet requires squeezing those particles together under tons of pressure, which holds them together very tightly. So tight that it would take the force of a hammer to break them apart. If we're going to get the drug particles out of the tablet when we swallow it, there must be something in there to help, because we can't very well swallow a hammer. Fortunately for us, the pharmaceutical scientists in charge of designing tablets use an ingredient called a disintegrant to help. Let's go back to the picture of the tablet as a stained glass window. Remember, the drug particles are the green pieces, which is what we need to separate from all of the other pieces after we swallow it. Let's imagine that the red pieces represent the disintegrant particles. These are made out of materials that love water, so much so that after you swallow a tablet, these disintegrant particles suck water into the tablet from the fluids in your gastrointestinal tract, and that's when they get down to business. A disintegrant, when it comes into contact with water, will begin to swell, which breaks all of those tightly bound particles apart. In a way, it's like a tiny explosion. You don't feel or hear it, of course, and it's not dangerous, but it has the effect of unjoining the particles from the tablet, enabling them to individually contact the gastrointestinal fluid. When freed from the confines of the tablet, the drug particles, which are still too large to get across those special cells in your small intestine, dissolve into individual drug molecules. Once in solution, that's when the drug molecules can be absorbed by the body, enter the bloodstream, and get to where they need to go. In the experiment that we have prepared for you, we're going to watch this on a slightly larger scale. The differently colored tablets that we have are much larger than anything that you would swallow as a medication, but that's just so that you can observe what's going on. When you drop the tablet in water contained within the test tubes, you'll note that the tablet begins to fizz. This occurs because tiny pockets of air are being released as the tablet begins the process of disintegrating. The tablets will get smaller and smaller as more of the particles are released from them, and eventually they will dissolve their molecules into the water. When they're done, notice how the water has changed color. The tablets are gone, but the coloration of the water tells us that the individual molecules have been released and are now hanging out with the water molecules at a scale too tiny to see. Who knew so much was involved in delivering a drug molecule?